Let's dive into part E together. Part E is interesting. Now, it looks more like A and B, but watch what happens when we try to work on this one. When you work it out and you add 2, you get, and divide by 3, we get sine x equals 2 over 3. Now, we do know that sine certainly can get to a height of 2/3. In fact, if you just think about the unit circle, I've kind of split this into thirds, right? And 2/3 is right here. There's definitely a possibility where that height, right, sine represents height, so where that height can get 2/3. The only question is, it's not going to be one of our nice special angles in the unit circle that we just know what the angle is to get 2/3. That's where in these situations our calculator turns out to be a handy tool. And this should look like something you have actually done in the past, usually in a geometry course or something. If sine x equals 2/3, and we don't actually know the exact angle that's going to get me there, I want you to remember something here though. We're not working in degrees right now, we're working in radians. And you have to change the mode of your calculator. On mine you press shift, and over here there's mode. And then you can choose radians. So if I want to solve this, remember that I just used the sine inverse of, so x equals the inverse sine of 2/3. Now if I want to be the most exact possible, I would actually just leave that. But we want something a little bit more tangible. So if I put in sine inverse of 2/3, what it's going to get me here is about 0.73 radians. And remember, a radian represents how many radiuses you've gone like around the unit circle. So it's not quite one radius, it's like 3/4 of a radius. So this is about 0.729, I'll just say 0.73. Okay, so we're saying is this distance is 0.73. We know that this is pi, which is about 3.14, right guys? Now here's the only other thing is, remember how there's actually technically another angle, or that gives an equivalent sine value over in that quadrant? This is where it's important to actually use some symmetry that we know in the unit circle, because we can't just be like looking at my unit circle, it's that one and that one. The interesting thing is, whatever this angle was right here, if we look at this triangle, that angle's the same, right? But what we're interested in here is, remember the angles are always measured from the positive x-axis. We actually want to know this distance, right? This space. So what we can do though is, since we know pi is the whole thing, and we know that that's 0.73, so that means this is 0.73. If I want to know that whole thing, then I can say pi minus 0.73 will get me my other solution. Okay, so again, if I just subtract pi minus this piece, it'll get me that other arc that I want to know the length of for the solution. So I'm going to do this, and I'm going to take my answer that I just got, and I'm going to do pi minus that answer, and it's about 2.41. And that looks like it makes sense, because if the whole thing is pi, 2.41, that looks about right. All right, we have a couple more equations to dive into, and then one last identity, and that'll be it. So I decided to give you actually one more I added in here to practice part E that we just did. So this is one I actually want you to pause and work on that yourself, and then we'll dive into these other quadratic style ones. I've set up one thing for you to remind you though. This one instead is cosine, and I think we can all agree that if we solve this, we get cosine x equals 1/5. Which yet again we agree, cosine can be 1/5 at some point, but again it's not one of those nice angles that we just know what the angle is, right? So we're going to have to use what we just thought about. In this case though, I split this into fifths, so wherever cosine x is 1/5, right, my overness, it's going to be about there on the unit circle. I've almost, because when cosine is 0 is when we get up here to pi over 2, right? But it's not quite there. So why don't you go ahead and pause and find, remember there's two solutions, and the other one's not going to be in this quadrant because it's cosine, it's going to be in a different quadrant. Take a stab at this yourself and then we'll do it ourselves together. So this is what you should have gotten for that. For cosine, it's other angle that would have 1/5 as the overness would be down here in quadrant 4, right? And remember, since we measure all the way around here to get the angle, it's not just that, okay? Once we do the cosine inverse of 1/5, we get about 1.37, and that's the arc right here. And that makes sense. That looks about 1.37 in comparison to this being pi, right? But then this much is also that 1.37. So if I take the full rotation minus that, I'm going to get what I'm actually looking for this one. Remember, we're matching it all the way around there. So if I do 2 pi minus that, I get about 4.91 radians for that, okay? So that's how we tackle these. I wanted to make a quick mention of something actually that I didn't give you this equation. What if this was flipped around? What if we tried to solve an equation and it ended up being like cosine x equals, the other one was 2/3. What if we had 3/2? We've talked about this a little bit. Just to remind you, if you end up getting something that's bigger than 1 over here, remember it can never get there, so there's just no solution. Just a little mention. Now let's dive into looking at the rest of these examples here. So this guy here says 2 cosine squared x plus 5 cosine x plus 3 equals 0. Hopefully that looks familiar to you from earlier in our very first warm-up examples we did in number 2. Well, number 1 and number 2 involved looking at these things. So these are basically compositions of a quadratic function with a sine or cosine put inside of it, right? And so we're going to actually deal with them like we would a quadratic first, and then take care of the trigonometric part of it afterwards. So we kind of already saw that we could think of this as like 2y squared plus 5y plus 3 equals 0. And we came up with the factorization of that already. It was 2y plus 3 times y plus 1. But if you remember, in this case, our y, right, is cosine x. So 2 cosine x plus 3 times y plus 1, so cosine x plus 1 equals 0. So again, we just turned this into a quadratic, or it is a quadratic, and we just thought of this cosine x as its own chunk, right? And so really we're just factoring a quadratic here to do this. Then what we get here is 2 cosine x plus 3 equals 0, or cosine x plus 1 equals 0. So keep going with this. This leads to cosine x equals -3/2. And actually that looks like something we just saw. This is outside of our range from -1 to +1. So this, I'm just going to put a big old X there. There's no solution for that. Or although actually, you know what we'll do? We've talked about this before. That symbol often just means no solution as well. And this leads to cosine x equals -1. And we can think, okay, well, when does cosine x equal -1? There's actually only one angle on the unit circle that works, and that's going to be at x equals pi. So my only solution for this equation here, this may have had other ones, but it didn't. My only solution ended up being x equals pi. So go ahead and do h and I on by yourself, and I will put down the work and come back together with you and look at that. All right, so here's all the work for these. Now these are going to incorporate elements of everything from today, so I totally understand if you're still processing and stuff. We'll even have a chance to be talking about this at some point, and we can dialogue, so don't worry about that if this was still a little bit of a challenge. First thing to note is that every quadratic always needs to be set equal to 0 in order to do anything. And you'll notice that this looks just like our next one that we already factored earlier, right? And then this one looks like our next one that we factored following that. Now, these boil down to sine x equals 1/2, which just is nice on the unit circle, and this one also has sine x equals -1/2, which is also some nice values on the unit circle. But each of these also has one that we have to tackle, just like the ones that we did here in part F, or E and F before, right? So this became sine x equals -2/3. And that's weird because their calculator spit out negative about 0.73. And that's because on the unit circle, when sine is negative, 4/5, it's going to be somewhere around here. So this distance of that arc is about 0.73 in length. So if you keep that in mind, you can see if I want the whole angle, and remember the actual angle itself is measured from there, actually a little further, then we need to subtract it away from 2 pi to get one of those, which is about 5.55 radians. But then the other option, remember, is reflected over here, and you can see that based on the symmetry here, that right there is the 0.73. And if I add that to pi, then I get my 3.87 right there, about. Okay, so hopefully that cleared it up if it was still a little bit of a struggle there. And then number 10 here, same deal, we got one that's easy, and then we got this one that's a little bit more of a challenge, although maybe not as much of a challenge as that one was. When sine x is 4/5, another imagining the unit circle, 4/5 for sine is about here, so it's going to be about this much of the arc, but then there's another matching one over here, right? And I'd have to subtract that away from pi, so I get 0.93 in my calculator for this much of that arc. But then the other one here, I want that much. So if I take pi and subtract that 0.93, we get that. Okay? Again, don't worry. There will be plenty of question time. There will be plenty of opportunity to keep practicing or ask questions about this. And one last thing for this lesson before we leave, and we'll be done with this lesson. All right, so one more identity I promised to show you called the Pythagorean identity. And again, we've hinted at it already. So I want you to think about here, if we just have some angle theta, then here's the terminal point, right? Here's the point that it intersects on the unit circle. And of course the coordinates of this point, its overness is cosine and its height is sine, right? So it's x and y. The cool thing here is that since this forms a right triangle, then we all know there's a relationship between the three sides, that the two legs, when you square them and add them, equal the hypotenuse squared, right? A squared plus b squared equals c squared. So here what we can say is sine squared theta plus cosine squared theta equals 1. And that happens to be true no matter what. Okay? That's a really nice identity. I want to point something out. We're only in quadrant 1 here, but what happens if I move over here into another quadrant? Well, even though the cosine is now negative, let's just say in this quadrant, the sine's still positive, the cosine's negative. It may be a good question to ask, well, is that going to affect anything? The nice thing about this is, because of the fact that we're squaring when we apply the Pythagorean theorem, even the negatives, once they're squared, still become positive, just as if it was in quadrant 1. So it doesn't matter what quadrant we're in, this rule still holds. So let's apply this to a couple things. These kind of count as equations, but I want you to notice something. We are not asking to find the angle anymore, okay? Now we've learned we could do that even for a weird one like this in our last examples, but all this is saying is find possible values of cosine theta. It's just a simple application of our Pythagorean identity, actually, because we know that sine squared alpha plus cosine squared alpha equals 1, and we know that sine alpha is 0.4, then we know 0.4 squared plus cosine squared alpha equals 1. And if I deal with this, 0.4 squared is 0.16, and so cosine squared alpha and 1 minus 0.16 is 0.84, and therefore cosine alpha could be equal to plus or minus. Remember, once we square root both sides, there's two possibilities, right? The square root of 0.84. Now your calculator might also say, it'll simplify for you nicely. Root 21 over 5 would be the actual full simplification of that, okay? Now remember, we didn't even ask for what the angle is. We're just saying if you know sine, can you know cosine? That's what's really good about this, is if we know sine, we can find cosine. And if we know cosine, we can find sine. So that's the purpose of this, of that identity that makes it really helpful. And you may write that down. If we know sine, we can find cos. If we know cos, we can find sine. Let's go ahead and do this one. Again, you can pause and work through it yourself real quick. but let's look at this one. This is going to result here in, we have to do something. Cos beta minus 4 is negative 2, so equals negative 2 over 3. So what we're saying is, if we know cosine beta is negative 2 over 3, what are the possibilities of sine beta? Well, again, sine squared plus cosine squared, so I'll just jump to that step right now, equals 1, and then we just solve for sine beta. And again, we're not solving for beta at this point, just sine beta. So sine squared beta equals, this becomes 4 over 9, and 1 minus 4 over 9 is going to be 5 over 9. And so sine beta is equal to plus or minus square root 5, right? If I square root this thing, that becomes 3. So root 5 over 3. And there's the full shebang. That was a long one, but now we have all the tools we need to deal with these, especially when we come up to some applications and stuff where these are used later on. So happy math, and we'll see you next lesson.